Good day, everyone. I'm Justin L. Sangol from BSED Math 3A. So today, I will present my final project task number 5, which is the permutation group. So this is my geometric model, which is the octa starlight. And this is the front and the back. And let P be, or let the row be the permutation for rotation. And row 0 is do nothing. Row 1, rotate 45-degree counterclockwise. Row 2 is rotate 90-degree counterclockwise. Row 3, rotate 135-degree counterclockwise. Row 4, rotate 180-degree counterclockwise. Row 5 is rotate 225-degree counterclockwise. Row 6, rotate 270-degree counterclockwise. Row 7, rotate 315 counterclockwise. And let mu be the permutation for lines of symmetries or the flipping. So mu1 is flipped vertically, mu2 is flipped between left diagonal and vertical axis, mu3 is flipped about left diagonal, mu4 is flipped between left diagonal and horizontal axis, mu5 is flipped horizontally, mu6 flipped between right diagonal and horizontal axis, mu7 is flipped about right diagonal, mu8 is flipped between right diagonal and vertical axis. So now this is the new front and the back of my Octa Starlight. So now, so for row 0, so do nothing. So we will operate the results to the original. So 1 is to 1, 2 is to 2. So from result, 3 is to 3, 4 is to 4, 5 is to 5, 6 is to 6, 7 to 7, and 8 to 8. So here we will operate the result to the original. So row 1, which is the 45 degrees, rotate 45 degrees counterclockwise. So from results to original. So 1 to 8, 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5, 7 to 6, and 8 to 7. So that's for row 1. So row 2, 1 to 7. So from result to original again. 1 to 7, 2 to 8, 3 to 1, 4 to 2, 5 to 3, 6 to 4, 7 to 5, and 8 to 6. So next movement is row 3, which is 135-degree counterclockwise. So row 3 is equal to 1 to 6, 2 to 7, 3 to 8, 4 to 1, 5 to 2, 6 to 3, 7 to 4, and 8 to 5. And the next movement is rotate 180-degree counterclockwise. And row 4 is equal to 1 to 5, 2 to 6, 3 to 7, 4 to 8, 5 to 1, 6 to 2, 7 to 3, 8 to 4. And the row 5 is equal to 1 to 4, 2 to 5, 3 to 6, 4 to 7, 5 to 8, 6 to 1, 7 to 2, 8 to 3. And row 6, which is the rotate 270-degree counterclockwise, row 6 is equal to 1 to 3, 2 to 4, 3 to 5, 4 to 6, 5 to 7, 6 to 8, 7 to 1, 8 to 2. And for last rotation, which is rotate 315-degree counterclockwise, the row 7 is equal to 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, and 8 to 1. Now for flipping or the mu. So mu1 is equal to 1 to 1, 2 to 8, 3 to 7, 4 to 6, 5 to 5, 6 to 4, 7 to 3, and 8 to 2. And for mu2, which is flipped between right diagonal and vertical axis. So mu2 is equal to 1 to 2, 2 to 1, 3 to 8, 4 to 7, 5 to 6, 6 to 5, 7 to 4, and 8 to 3. The next movement is mu3, which is flip about right diagonal. So mu3 is equal to 1 to 3, 2 to 2, 3 to 1, 4 to 8, 5 to 7, 6 to 6, 7 to 8, and 8 to 4. The next, so mu4 is flip between right diagonal and horizontal axis. So mu4 is equal to 1 to 4, 2 to 3, 3 to 2, 4 to 1, 5 to 8, 6 to 7, 7 to 6, 8 to 5. Mu5 flip horizontally. So mu5 is equal to 1 to 5, 2 to 4, 3 to 3, 4 to 2, 5 to 1, 6 to 8, and 7 to 7, 8 to 6. So mu6 is split between left diagonal and horizontal axis. So mu6 is equal to 1 to 6, 2 to 7, 3 to 8, 4 to 1, 5 to 2, 6 to 3, 7 to 4, and 8 to 5. The next is mu7, split between left diagonal. So mu7 is equal to 1 to 7, 2 to 6, 3 to 5, 4 to 4, 5 to 3, 6 to 2, 7 to 1, and 8 to 8. And for mu8 is flipped between left diagonal and vertical axis. So mu8 is equal to 1 to 8, 2 to 7, 3 to 6, 4 to 5, 5 to 4, 6 to 3, and 7 to 2, and 8 to 1. And now that we already get the results of the permutation, let binary operation star be the operation under multiplication. So now we will use the operation, which is the multiplication. So let's try some example to demonstrate how to operate. So here is the example. So row 4 times row 2, so is equal to, so here when we are multiplying some or two elements, we will start to operate from the second one to the first one. So the underlined one is, we will operate the underlined one to the first one. So 1 7 7 3. So that's why the one is equal to 3. And 2 to 8 is 8 to 4. That's why it's equal to 2 to 4. And 3 to 1, and here's the first, it is 1 to 5. That's why the answer is 3 to 5. And 4 to 2, and here to the first one is 4 to 8. The answer is 4 to 6. And here 5 to 3, so 3 to 7, and 6 to 4, and 4 to 8, and 7 to 5. Here 7 to 3, so the answer is 7 to 1, and 8 to 6 is 6 to 2. So when we operate row 4 to row 5, we will get the value of row 6. Now let's move on to the next example, which is row 6 times row 3. So here is the value of the row 6 and row 3. Now we will operate the second value, which is the row 3 to row 6 to the first value. So here 1 to 6, and the first element here, or the 6 to 8, and that's why the number 1 here is 8. And 2 to 7, and 7 to 1, that's why the 2 is 1. 3 to 8, 8 to 2, 4 to 1, and 1 to 3, so 4 is 3. And 5 to 2 is 2 to 4, that is 5 is, that's why that 5 is 4. And 6 to 3, and 3 to 5, 7 to 4, 4 to 6, and 8 to 5 is 5 to 7. So when we operate row 6 to row 3, we will get the value of row 1. And now that we already know how to operate the multiplication here in permutation with the two elements, we will do this from row 0, row 1, row 2, row 3, row 4, row 5, row 6, row 7, and mu1, mu2, mu3, mu4, mu5, mu6, mu7, and mu8. So that's why I will just show you the answer that I get when I operate them. So here is the P0, row 0 and row 1, row 2 and row 3, row 4 and row 5, row 6 and row 7, mu1 and mu2, mu3 and mu4, mu5 and mu6, mu7 and mu8, and that's why we get this table. Now, this table, we will check if this is group. So we will also look for if we will also look for as isomorphism, or we will look if this table is isomorphic to the table that we made or we made the in the past task 1. So now let's check if this is a group, which is closed, that has associative and has identity element and has inverse. So here is the octa starlight a binary structure? Is it closed? And this table is closed since we operate two elements with each other. The resulting elements is always found in the element in the table. So yes, it is closed. Now we will check for the associativity. So when we are checking for associativity, we will rotate it first to 180 degree. So here is the face of the table when we rotate it to 180 degree. So as you can see that when after rotating 180 degree, and it's not the same anymore to the original table. So what we're gonna do is interchange some to column or rows to make it the same or equal. So first we will interchange the second and eighth column, which is the row 1 and row 7. And second, we will interchange the third and seventh column, which is row 2 and row 6. Third is we will interchange the fourth and sixth column, which is the row 3 and row 5. Fourth, we will interchange the ninth and 15th column, which is the mu1 and mu7. Second is we will interchange the 10th and 14th column, which is the mu2 and mu6. Sixth, we will interchange the column 11 and 13, which are the mu5, mu3, and mu5. So after the 180 degrees rotation and the interchanging, these two tables are equal or the same. So as you can see here, they are equal and they are the same. This means that this means that this table has an associative. So check. So next we will check for identity element. So here, as you can see in the table in column 2 and row 2, when the element is being operated to the P0, and the element that is the resulting element is the same or itself. So like here, P0 star P0 is P0, P1 star P0 is P1, P2 star P0 is P2, until to mu8 star P0 is mu8. That's why we can conclude that the identity element in this table is P0. So it has an identity element. Next, we will check if there exists inverse element for all. So you all know that when we are checking for inverse, and we will look for an element that if we operate to one another, the resulting element will be the identity element. So to make it easier, we will just look at the table to the identity element. So P0 here, P0, the red P0, it is the identity. So from row here, P0 star P0, which is equal to P0, that's why the inverse element of row 0 is row 0. And the inverse element of row 1 is row 7. The inverse element of row 2 is row 6. The inverse element of row 3 is row 5. The inverse element of row 4 is row 4. The inverse element of row 5 is row 3. The inverse element of row 6 is row 2. The inverse element of row 7 is row 1 until the row 8. So as you can see in the table, the identity element exists. So that's why it's also correct. So the condition for a group structure, a binary operation, check. G1, it is associative, check. G2, it has identity element, check. G3, it has inverse for all, check. So meaning, therefore, it is a group structure, and we found out that the table that we made in task number 1 and the table that we get here in the permutation is isomorphic.